Hey everyone. So in this video, our closing video of the entire school year, we are going to look at how you find the distances between things, specifically when we're in the frame of mind of vectors. So the first one would be a point and a line. How do we find a distance between a point and a line? Well, first, if we think about what would be going on in that situation, here's a point and a line. If you're figuring out the distance between a point and a line, what we mean is the smallest distance. Sometimes they even say that. What is the shortest distance between a point and a line? Because otherwise, people could say, well, this is the distance. Well, that's not really what we mean. We want the closest distance. So we want this distance right here. What is the distance between that point and that line? So let's actually try one. Let's say we had 1, comma 2, comma negative 1. And let's say that the line we had was XYZ. How about 3, 1, 2 plus lambda? Now let's do plus t. My lambdas get weirder looking over time, so we're going to be writing that a few times. So let's go negative 1, 2, 1. Okay, so let's say we want to figure out the minimum distance, which is shown in the diagram, between that point and that line. Well, I think you would agree that any point on this line could be thought of as just x, y, z. So if we wanted to think about it in terms of like a more traditional way of writing a point, we could think of the x coordinate as being 3 minus t, the y coordinate 1 plus 2t, and the z coordinate 2 plus t. Now I know that's not where we want the point to be. We want the point to be here. But there's no, how do we find that point, right? How do we know that that's the point we have? We don't. So this here represents any point on this line. Well, think about what else we know about finding distances. We know the distance formula. So if we use the distance formula and substitute in what we've got, I have 3 minus t minus 1 squared. So I subtract x1 minus y1. And then I have 1 plus 2t minus 2 squared. And then I have 2 plus t minus negative 1, so plus 1 squared. That's going to be our distance for any value of t that I have. So if I multiply that out, I'm going to have 2 minus t squared, so I'm just simplifying a little bit here, 2t minus 1 squared, mt plus 3 squared. What we are going to do is we are going to say, well, this is going to look like the graph of a parabola. And if we want the smallest distance between a point and a line, then that would be, if I graphed this, the minimum value. How do we find a minimum value? We take the derivative and set it equal to 0. But I actually am going to suggest that we don't take the derivative of d. I'm going to suggest that we take the derivative of d squared, which I accidentally prematurely wrote. Because if we do that, we'll end up with the same answer either way. And if we take the derivative of d squared, now the radical's gone. So I'm going to get 4 minus 4t plus t squared plus 4t squared minus 4t plus 1 plus t squared plus 6t plus 9. I'll add like terms up here. I have a t squared, a 4t squared, and a t squared. So 6t squared, negative 4t, and 6t, so minus 2t. And then I've got 4 plus 1 plus 9, so 14. So I'm going to take the derivative of that. So the derivative with respect to t of d squared. So I'll get 12t minus 2. And I want to know, where is that equal to 0? Add the 2 divided by 12, I get 1/6 equals t. So what I can do now is I can plug that in to my line to get the actual point of where that will be. So that will be the point that's closest to, and then I just go back. Actually, I could just skip that and plug back into here if I wanted to, because what we really want is the distance, right? So if I plug my 1/6 back in there, I will get the distance. So 2 minus 1/6 is 11/6. Here I'll have 2/6 minus 1, so that'll be negative 4/6. And here I'll have 1/6 plus 3, so 19/6. So I'm going to have a common denominator of 6 when all is said and done. So I'm just going to work out the numerator here. So I'll have 121 plus 16 plus whatever 19 squared is. That is not one I know off the top of my head. Some of you probably do. 361. So all the 6's on the bottoms are squared, so that'd be 36, and then you square root to get 6 again. So 121 plus 16 plus 361. So radical 498. I don't know how much that simplifies, but we're going to leave it at that. So that's how we can find the distance, the perpendicular distance, which is what they want when they say distance, between a point and a line. Okay, let's move on to the next idea. What about if we want two parallel lines or two skew lines? What if I want to find the distance between two lines? The distance between two lines, whether they are parallel or skew, either way will work here. So I've got two lines. I'll look at the parallel case just because the skew case is very hard to draw on the paper. So we're going to have these two lines here, right? Let's say we have xyz equals 1, 2, 1 plus t, negative 1, 4, 1. And let's say I have this other line here, xyz equals 0, 3, negative 1, plus let's do s. Let's do p. My s's look like 5 so much. And let's do 1, negative 2, 2. Okay. So these are not parallel because their direction vectors are not scalar multiples. But for the purposes of the picture, I kind of drew them that way so that we could explore. Well, we kind of have the same scenario going as before. Actually, yeah, we'll do the parallel case first. So let me change this to make it parallel. So I'm going to scale it up by a factor of 2. So I'll do negative 2, 8, 2. Okay. So if we we can think of this situation as being similar to the last one. All we need is any point on one of the lines, and then we need to find out the distance between that point and the other line. So any point on that line is going to have the same distance because parallel lines are always going to have the same distance. So it does not matter what point we pick on this line here. So that's the first thing I'm going to do, is just find a point on one of the lines. I think I'll do the second one. I'll just plug in a 0. P equals 0. At P equals 0, we have the point 0, comma 3, comma negative 1. So maybe that's this point here. And so now what we want to do is the same thing we did last time with the same set of steps. And I think I'm not even going to work that out completely. So you do the same steps we did last time using this point and this equation for your line. Okay, let's look at the distance between, we're going to get back to the distance between two skew lines. Let's look at the distance between, what's up next? Let's do a point and a plane. A distance between a point and a plane. Here's our plane. Here's our point. I want to know how far is that point from the plane. So let's say that that's perpendicular to the plane. Again, anytime we measure distance from something to something else, we want to know how far it is in a perpendicular way. We're not going to go off to the side like this. we're going to go perpendicular to the thing we're measuring the distance to. So as you might guess, this is going to involve the normal to the plane, because that's what we do when we want things to be perpendicular to planes. We talk about normals. So what we're going to do is we're actually going to use, let's give ourselves an example here. Let's say we have 2x plus 3y minus 4z equals 2. Let's say that's our equation for our plane. And let's say we have the point 5, comma, negative 1, comma, 7. And that's our point. So there's actually a formula that we can use. This is not in your booklet, so you will want to memorize this formula. And the formula we can use is going to take the A, B, C, and D from the equation of our line. So notice that the way we are coming up with A, B, C, and D for this formula is by moving the D and having a 0 on one side. So our D in this case is actually going to be negative 2. And then we're going to call this point up here x1, y1, z1. x1, y1, z1. So A, B, C are the coefficients of the x, y, and z terms. D is the constant, but if it's been moved over. And then x1, y1, and z1 are the point. So the formula that we can use to find the distance, we're going to take the absolute value of A times x1 plus B times y1 plus C times z1. So we're basically doing the dot product between the coefficients and the point up here. But then we are actually also adding in D. I'm not going to do the proof of this formula just because of time. We've got a lot to fit in, kind of out of time in terms of like getting ready for our exam. So know that there is a proof, but we're not going to worry about it. And then you're going to divide by the square root of the distance of the normal. So a squared plus b squared plus c squared. So you're using the distance formula for the normal on the denominator. And then once we fill those things in, we just evaluate. So memorize that formula for distance. It's not in our booklet. And I think the reason it's not is because there is another way to do this, but it takes way longer. And so I think this is probably just, we can memorize a formula. That's not going to be that bad. And this should be minus 2. Okay. And then divide by the square root of 4 plus 9 plus 16. So this is the absolute value of the dot product minus the D value. It's kind of weird in there. So we get 10. Now we're down to 7. 7 minus 28, go. Negative 21 minus 2. So we're negative 23, but we're taking the absolute value of that. So positive 23 divided by rad 29. So if you wanted to rationalize that, you could. IB really doesn't care, but you're used to it. So you might want to write 23 rad 29 over 29. Okay, so that's how you find the distance between a point and a plane. Next up, the distance between two planes. And when you're finding the distance between two planes, they have to be parallel. Either planes are parallel or they are intersecting. So if they're intersecting, the distance between them would be 0. But if they're not intersecting, they would be parallel. And so we have this situation. And we want to find the distance between these two planes. Well, what we want to do, similar to how we reduced the problem about two parallel lines down to the distance between a point and a line, we can do the same thing here. We can reduce the distance between two parallel planes, to the distance between a point and a plane. So we just need to find any point on one of your planes. Need any point on one of the planes. And then we do what we did above. So we would be needing the perpendicular distance, which is going to be your normal vector, or the normal vector to that plane. So two parallel planes. Let's say this plane is 7x minus y plus 2z equals 14. And this plane is negative 14x plus 2y minus 4z equals negative 29. If these are exact scalar multiples, the entire thing, even the constants, remember that would be coincident planes, where it's just the same plane twice. So we definitely want to make sure that's not happening. We would figure it out, though, pretty quick when we did the math, though. So this, we have a scalar multiple, negative 2. So these are parallel planes. And once we know that they're parallel planes, we can do what I was just saying. So my suggestion, we need any point on either one of these planes. My suggestion is to make a point where two of your values are 0. So I'm just going to say, well, x is 0 and y is 0. What would z have to be in order for this to be true? If this was 0 and 0, z would have to be 7. So make two of the values 0, and then figure out what the third one would need to be on the plane. Okay, and now we repeat the steps from before. So we've got our A, our B, our C, and our D will be 29. And now we repeat the steps. So we're going to do the absolute value of the dot product between the normal and our point, but then with the plus 29 in there. And then divide by the square root of whatever 14 squared is, 196, right? Plus 4 plus 16. Now, this part, a lot of that simplifies out, so we end up getting negative 28 plus 29, so we get 1 over rad 216. I'm pretty sure that's divisible by at least 4, if not divisible by 16. Yeah, it's divisible by 4. So if you can simplify, you should try. It may not be worth your time at that point to worry about simplifying a radical. You might just want to move on, but that would be the distance between those two planes. Okay, and we have one last situation to look at, the distance between skew lines. The distance between skew lines. And this is our last example for the whole school year. Okay, so let's come up with some skew lines and look at what process we're going to use. We're actually not going to quite use the same process as the distance between two parallel lines. It's going to be a bit of a different process. It actually isn't going to involve distance formula at all. Okay, here's what we are going to do. So let's say we have one line, and then we have another line that's in a different plane as that first line. So don't picture these lines as intersecting eventually. Picture this one as like lower and this one's higher in the air. And there is a line between them that would be perpendicular to both. There's a sweet spot where those two lines are going to be as close as they ever get. And this place where they're going to be as close as they ever get are going to be able to be connected with lines that are with a line or a vector, whatever you want to call this green guy, that is perpendicular to both. Okay, we are going to figure out what that distance is. What is this distance right here? Okay, so what we're going to do, let's come up with two lines first. So let's say we have line 1. Did not mean to put that dot there. Line 1, let's say that it is x equals y minus 2 over negative 1 equals z minus 2 over negative 1. And let's say that line 2 is x minus 2 equals y minus 1 over negative 1 equals z plus 1. So these are the two lines that are skew, and we are going to figure out, and so they do not intersect. and we're going to figure out what the smallest distance is between them. So first thing we're going to do is we are going to set each one equal to some parameter. So I'm going to use t and p like I did on an earlier example. And so what I'm going to do is I'm going to write each of those out in vector form. So I'm going to get 0, 2, 2, plus t, 1, negative 1, negative 1. And then over here, I'm going to get 2, 1, negative 1, plus p, 1, negative 1, 1. So those are the equations of my lines. Now what I want is I want a line that is perpendicular to both of these. So I'm going to call this point A and this point B. So I need some representation for A, B. Well, if I think about what A and B are, A would be, let's say that line A is on line 1, and let's say that B is on line 2. So the x value for A would be 0 plus 1t, 2 minus t, and 2 minus t. Whereas the coordinate for point B would be 2 plus p, 1 minus p, and negative 1 plus p. Those would be our x, y, and z coordinates. So if I wanted to come up with a vector for AB, I would simply subtract b minus a. We've done that before. So I'm going to get 2 plus p minus t, 1 minus p minus 2 plus t, if I distribute my negative, and negative 1 plus p minus 2 plus t. Again, distributing the negative. And I'm going to simplify that a little bit. 2 plus t minus p, negative 1 minus p plus t, and negative 3, did not mean to put a parentheses there, I meant to put a comma, and negative 3 plus p plus t. So this is vector AB. What did we say needed to be true about vector AB compared to each of the other vectors? It needed to be both, let me make sure, I feel like I made a mistake here. I'm going to pause and make sure I do not make a numerical, like a calculation mistake. Okay, don't think so. Okay, so we know that this AB needs to be perpendicular both to line 1 and it needs to be perpendicular to line 2. So how do we determine if something's perpendicular with another line? Two vectors are perpendicular, we find the dot product, right? So the dot product between each of these pairs of things needs to be 0. So if we do vector AB dotted with line 1, it should turn out to be 0. And vector AB dotted with the direction vector, I should be a little more careful with my. So dotted with the direction vector from line 1, then dotted with the direction vector from line 2 should also be 0. So we're going to get two equations with two variables. The two variables are going to be p and t, and then we figure out what p and t are, and then we can find the distance. So let's do that. Okay, so we have AB dotted with D1s, this direction vector here. So I'll do that work over here. So I need 2p, 2 plus p minus t times 1, plus 1 minus, sorry, I rearranged it, negative 1, I'll use this one, negative 1 minus 1 plus t, dotted with negative 1, and then negative 3 plus p plus t, dotted with negative 1. And we know that that's going to equal 0. So now what we do is we simplify that as much as we can. Collect my like terms here. So I get p minus 3t plus 6 equals 0. Now I want to do the same thing with AB dotted with D2. So here's my D2. vector. Here was my D1 vector. Okay, so same deal. I'll do 2 plus p minus t times 1 plus negative 1 minus p plus t times negative 1 plus negative 3 plus p plus t times 1, and that should equal 0. Add like terms, so I have 3p minus t equals 0. And so now I want to solve this as a system of equations. So if I multiply this by negative 3, I'll get negative 3p plus 9t, and then we've got minus 18 equals 0. So I'll get 8t equals 18. So that's going to be 9/4 for my t. Okay, so now I can substitute that in and find s, or p, sorry. I'm used to making it t and s, but my s's look so weird. So I'm going to substitute this in. So I'll get 9p equals 9/4. So p is going to, 3p equals 9/4. So I'm going to get 9/12. So 3/4. So I have a p of 3/4 and a t of 9/4. So how does this help us? Well, once we know what the parameters are, we can now go and figure out what vector AB actually is with not just p's and t's, but with actual numerical values. And then we know how to find the magnitude of a vector. We just use the Pythagorean theorem. So I'm going to substitute in p equals 3/4 and t equals 9/4 into vector AB and see what we get. So we had 2 plus 3/4 minus 9/4 for our x component, negative 1 minus 3/4 plus 9/4. I didn't mean to put a comma there. And negative 3 plus 3/4 plus 9/4. Order doesn't matter in that case. So for vector AB, if we simplify that all down, we're going to get a half, right? Because I'm going to have 8/4. So 8/4 plus 3/4 is 11/4, minus 9/4 is 2/4. So I get a half. For my y component, also a half, because I end up with negative 7/4 plus 9/4. So that's 2/4, so a half. And then here, this makes 12/4, which is 3. So that just ends up canceling. So vector AB is 1/2, 1/2, 0. And I want to know how far that is. What is this distance here? So I could then find the magnitude of vector AB by doing 1/2 squared plus 1/2 squared plus 0 squared, but that doesn't really make a difference. So I'll have the square root of 1/4 plus 1/4. So the square root of a half, which is the same as rad 2 over 2. So that would be the distance between these two skew lines. So a lot of material in there, a lot of different distance things, but it's using a lot of different bits of logic. So to recap, when we were doing the distance between a point and a line, just trying to find my original thing here, we said, well, one way of doing this is actually using calculus and saying, hey, if I find the distance, if I use the distance formula and I minimize the distance between them, that's going to give me the distance I'm looking for. Okay, so that happened when t equals 1/6. Then we looked at some examples where it was the distance between two parallel lines. We basically can use the same process. We just need a point on the line. So just plug in like 0 for one of your parameters, and then you got a point, and you figure out with the other line the same process that we did in the first example. Then we moved on to planes. And there's a handy dandy little formula that you'll probably want to memorize for the distance between a point and a plane, and the distance between two parallel planes. And lastly, the distance between two skew lines is this process here. So it's kind of a little bit more of a process than the rest of them, but that is how you can accomplish that. Okay, that wraps it up for, well, the school year.